next up, we have Dr. Braden Kelly. So Braden loves doing science experiments with a computer. What he says is that nothing really exists, yet the experimental observations are real, powerful, and useful to humanity. So Braden, you can teach us a little bit about that, and you can take it away.
So I'm going to be talking about the role of open source software in science and how it helps open up science for us. So to get started, I want to just go over how does software fit into science. So we're used to thinking of science as being composed of two pillars, one of them being theory and the other one being experiment. But with the advent of computers, there's actually a third pillar that's come into existence, and that's simulation. And so what simulation is it's the implementation of theory into a computer, allowing you to do experiments on the computer. And the software is what lets you do these experiments. So I also want to go over closed and open source. So a closed source piece of software is locked to you by default. You need a key, or more commonly, you need a product key. And this requires you to have to usually pay money. So you have to get your piggy bank out, you have to break it. And then once you've paid some money, then it's unlocked to you and you can use the software. On the other hand, open source software is unlocked from the beginning, and it's always available. And it's not just free, but it's open in the sense that you can also make changes to it. It's not a black box. So I'd like to give an example of open source software in science. And the example I'm going to give is the COVID Moonshot project. This is being run by a group called Folding at Home. And what it is they're trying to use computers to screen for better antiviral molecules to fight COVID. They do this using the OpenMM software. It does molecular dynamics. And COVID is a really big molecule. It actually, to do these simulations, requires essentially a supercomputer. And what they've done is they've managed, their supercomputer is volunteered from normal people. You can sign up, and when you're not using your computer, they will be able to run calculations on it. And the combination of all these computers is actually really huge. There's over 1 million volunteers. They've set a Guinness World Record as the largest supercomputer in the world. And in fact, it's faster than the top 500 supercomputers combined. And this is all made possible because from the ground up, everything is open source. You don't need 1 million licenses. Everything is free to use. So really, even non-scientists have been able to collaborate on this project. And that's a big issue. A big plus with open source is that it allows collaboration because everything's free, everything's open, and so everyone in the world has no barriers to it. The science is available for everybody. On a more technical side, when it comes to, for instance, research, when you're using software, often you have a question and you want to perform an experiment to get an answer. So if you're using closed source software, you ask this software your question. And if it's pre-programmed, if it knows how to give you the answer, it will. However, if you're doing research, typically your question hasn't been asked before. So the black box isn't going to be pre-programmed. So all you get back at the end is a question. It doesn't know, and you don't know the answer. And that's all you can do. You can't see in it. You can't make any changes. You're just at the end of that road. Usually the software takes many people, many years to make. So it's not like you can just make your own black box. However, this is where open source software comes in. With open source software, you can see inside the box. So if it doesn't do what you want, instead of reinventing the wheel from scratch, you can just look at it, figure out what's missing. You can add in that little piece, and all of a sudden, you have contributed to this program. You've added a piece to it. It will give you what you want. So you can ask it your question, and you will get your answer. And not only that, but everybody coming after you can also ask this question. And further, people could have a more complicated variant of your question, so they can add in their own gears to make it going. So really, the whole scientific community really collaborates on these software programs. And so you start with some core program, but very quickly everyone contributes to it, and it becomes much larger than anything you could have anything that really just a black box would be capable of doing. Finally, an important process in science is quality assurance, and we do this through peer review. So when you are a peer reviewer, you want to make sure that what you're reviewing is significant, original, that they give credit where credit's due, that they acknowledge those who came before them. And also, though, you want to make sure that their work is reproducible, because that's a key foundation of science. If you do the same things, you should get the same result. So if they're using proprietary software, this is very hard, impossible even to double check, unless you want to pay the money. But as reviewers, you're already working for free. So it's often you can't check. So this isn't you can't really guard against any errors. And so with that, I'd just like to conclude with what I do as a postdoc. I work in the group of Paul Ayers at McMaster. We produce theoretical chemistry, and we implement it in software packages. The biggest one we do is the Horton package. And that's what I work on, is coming up with more theories and implementing them as well inside the Horton package so that anyone can use them for free. Thank you.